start? So welcome to the Python Epiphanies tutorial. I'm Stuart Williams, and the exercises you'll see there, if you want to download those, if you haven't, please do. And the survey, really important that we get data for PyCon to help us improve the tutorials over time, at least measure how they're doing. So appreciate it if you'd fill that out eventually. So in this tutorial, I'm going to show you a bunch of code, mostly one-liners, and then I'm going to give you some time after many of the sections for you to do some one-liners, mostly one-liners, and explore the code. I'm assuming that most of you, the target audience here is that you have used Python for a while, so you don't need to learn the basics. You'll especially benefit if you used other languages for a long time and then started using Python, and you get to the point where you're like, I thought I understood this, but stuff keeps confusing me. So those are the people, that's the sweet spot, the ones who will really get the most from it, I hope, based on experience. And the reason I call it Python Epiphanies is because I'm looking for the aha moments in the audience. And based on the 5 or 6 times I've done this before, a lot of people get a lot of aha moments, like, oh, that's how that works. I will show you a bunch of bad code because I'm going to go poking around behind the scenes to see how Python works and show you some things you shouldn't do. But it helps you understand how Python works, and my hope is that by understanding that, it'll make some of the other things that might have been confusing you more clear, either why they're confusing you or they won't confuse you anymore. And had another thought which I forgot. So in the handouts that you have, the exercises, I will go through the code myself. The first 1 or 2 sections, it's going to feel really slow for most of you, and that's on purpose, because I'm going to be very careful about the language I'm using to try to make you think about the way Python works in a certain way. And that's to get rid of, for some of you, you've got a mental model that's not quite right, I suspect, based on, again, experience and the aha moments I've seen. So that's why we'll be doing that. When you get to the exercises, there'll be maybe, let's say, average 15. And the first few will be fairly easy, the next few a little harder, the last few pretty hard, like it'll take you a long time. So I'm hoping that no one gets through all of them. But that means if the fastest person in the room just barely finishes, that means the slowest person in the room is going to just get through maybe the first third, and then they're going to get frustrated because I'm moving you along. That's on purpose. So don't feel bad. Just expect not to finish all the exercise sections. During those, I will wander around, and Brandon and Back will wander around if you have questions, things that you're stuck on. I thought I had one other thought, but I think that's about it. So let's get started with looking at some code. Oh, yes, the other thing I wanted to mention is if while you're doing the exercises, don't feel that you have to do exactly what I told you in the exercises, right? I've designed it because I think it's pretty good for most of you to learn from the exercises, learn new things and reinforce what you've just learned. But if you find it's useless, well, skip to the end or do something different. That's fine with me. I do encourage you in the exercises to actually type them, not just do what someone else did, not just paste them. Okay. So first I'm going to do real basic stuff on objects, and some of you will be like, we know most of this already. So the way you create objects in Python, typically you would create them with literals, right? These over here are line numbers, by the way, they help me navigate when I need to move around. So when I type 1 at the Python prompt and I hit enter, I'm sorry, I've got timeout while I do a minor screen adjustment here. Thought I had this all figured out. You never can. There we go. Blank line's gone. Okay, so when Python sees a 1, it goes, that's literal. I know how to construct an object out of this. So it goes out and it figures out how to construct an integer object that represents an integer. It's got a bunch of stuff hung off it, which we'll look at later. And because we're operating at the REPL, the read eval print loop, it shows you the expression if it has a value other than none. It tries to print it for you. Okay, so we can do ints and floats and strings. You can also get a couple pre-created objects, a few that are built in, and we'll look at some of those later. True and false are 2 good examples. At the more fundamental level, let's just show you. Don't know why. Is it because the search window's open? Yes. Okay, so the fundamentals of objects in Python is every object has a single value, has a single type, has some number of attributes, one or more base classes, a single ID, and then it has names. And the names we're going to talk about in the next section. So, types. The type of that, class int, right? So the integer 1, that's its type. Type float, type string. Okay, there's a Boolean class now in Python. Actually wasn't originally. It's interesting to read some of the discussion that went on when people were arguing about adding that. Objects have attributes. So you can see the dunder doc attribute of the true object, I'll call it. The dunder add. Dunder is double underscore add double underscore. That's pronounced dunder. So dunder walk has this method wrapper attribute. So that attribute refers to an object. It is callable. We can actually call it and pass it. It's a method, so we're calling the method by passing an object. We call the method on the object, and we pass that parameter, and we get those two strings added together. Similarly with these, objects have base classes. All right, so let's look at a couple of these. Oh, why did that fail? So inspect is a module that lets you do a bunch of introspection in Python. Get MRO is get method resolution order. And if we pass it an instance of a class, it doesn't know what to do because an instance of a class doesn't have a dunder MRO attribute. But if we pass it the class, the type of the object, then it knows what to do, and it shows you that int is a subclass of object. Object is the superclass of all objects in Python. We can look at string. We can look at true. True, so bool is a subclass of int, is a subclass of object. Base classes happen to be stored in attributes, and here's where we'll start looking at some of these attributes to see how things are wired up behind the scenes. So you can see that there's the class is stored there. It's got plural bases, which is a tuple with a single value. We grab the 0th one and look at its bases, and we get object. So bool int object, just like we saw from get MRO. Every object has an ID. In CPython, the ID is the memory location. You don't need to know that. It's not always going to be true necessarily, but that's what it happens to represent. It is unique to every object. So two objects that are different objects will have different IDs. That's the only thing that's guaranteed. Yes. So the most common way we create objects in Python other than literals is we call functions like the absolute function, which is callable and will return us a positive int if we give it a -1. And remember, what's going on here is that Python sees the -3, creates a new -3 object if it doesn't already exist. It then looks at abs and goes and finds the object that the abs name refers to, and then it passes the first object it found to that abs function, and it calls it, and it returns an object, which happens to be another integer, the object, which represents the integer 3, and then it prints on standard output. Okay? Again, I'm going really slow just to make sure you're thinking about it this way, as opposed to thinking about slightly other ways, different ways of thinking about it. There's another built-in name, which is callable, so I can call it like a function, and it'll give me a new object. And there's the attribute, similar to another attribute of the string walk, and we can call it to get a new object. Call this one to get a new object. So that's the other way that we can create objects. Okay? So the reason I want you to think about the object creation is some of you have used languages where you declare a variable and it's compiled, it's a static declaration, type declaration, and the compiler sees that name and it sees the type declaration. It figures out how much memory to store on the stack, and it figures out what machine instructions to issue into the machine code that gets compiled into so that it can operate. So if it's an int, it'll issue int instructions. If it's a float, it'll issue float instructions. Python doesn't do that, right? So don't think of a box that gets allocated. Think of objects that get created out there somewhere where you don't have to know where they are on the heap somewhere. And Python worries about garbage collection, and it's the names that refer to them. So I'm going to hammer that in too in the next section. So take a couple minutes and look at the exercises and do them. I won't give you too long, and then we'll talk about them. I'll actually run through them all afterwards, so don't worry if you don't get through them. Sure. Make sure you holler if I say something wrong. If I make mistakes, let me know. I'll give you about 1 or 2 more minutes. I'm happy to entertain questions while you're working on them if you want. I think if you keep going, you'll see. Oh, well, no, here's why. I'll explain it to you. Yep, I'll explain it. Okay, let's look at these together, and I'll show you a few things. So, no surprise, dir is a function that lets you look at attributes of any object. It actually has a, we'll look at that, what dir does exactly a little bit later. Method wrapper, it's callable. We need to call it with at least one argument, well, with exactly one argument. Right? Now, for.add, all I'm showing you here, and I introduce errors, there are a bunch of, there's probably 30 or 40 errors in this whole set of stuff on purpose. Maybe not that many, maybe 20. On purpose to make you think about what's going on. What's going on here is it sees the for, it sees the dot, it goes, floating point number, and give me more, and then it says, I don't know what you're talking about, right? You put parentheses around it, you can do that. And there are a couple weird edge cases in Python to make a nice clean syntax. Then it sort of has to double up the use of some syntax characters, and in this case, that's how you get around, is put the parentheses around it, right? So get size of, we'll just shorten it to size. The reason I shorten these sometimes and try to keep the name short is so when you're typing, you're not spending all your time typing long stuff. So the size of the string w, not the character w, in Python, there is no character data type. It's always strings. Some of them only have a single character or 0. And you can see that a string object with only a single character takes 50 bytes of data. So when I say it's going to create some big object in memory that represents a string, and the same for int. I think I did an int here too, right? 28 bytes just to figure out a regular int. And then, so it's storing lots of other stuff in there. Now for the primitive types like int and string, not that much. It mostly just points to the parent class, the class of which the object is an instance, but it is storing some. So here we've got, there's size 28. Oh, there we went over the boundary, and there's another boundary where we're actually needing more memory to store these very large integers. So, any questions on that section? Okay, the next section, which is also going to be kind of slow because I'm going to want you to think about this a certain way. So don't lose hope if you're like, man, this is so slow. So names in Python refer to objects. As opposed to variables, which are pre-allocated and have a data type and instructions issued so they can get at the memory and do the right thing, names in Python refer to objects, okay? So think about names and objects, and a bunch of stuff in Python becomes more clear. So when you add a name to a namespace, it's like updating a dictionary with a new key. So I'm going to restart my interpreter, and I'm going to show you that there's nothing there, except I don't like that dunder built-in. So there. Dunder names for me, or sorry, underscore names for me, shows you all the current names I've added to the namespace. So if I try to access, say I get a name error, it's saying there's no such name, no key in the dictionary, which is my namespace. I can add a name to the namespace like that. Right? So what happened is Python saw the 300, created a new integer object, 300. It then saw the equal and the a and said, let me go look for the name a in the current namespace and make it a reference to the object 300 that I just created. Okay? That's it's really helpful to think about. That's what Python is doing. So people call this assignment. Go ahead. People talk about the variable a in a mathematical sense. That's true. But in the way many other languages use the word variable, it's very different. So it's just a name referring to an object. And you can see that there's the new dictionary entry that got created, right, for the name, the namespace. So it's got the key and it's got the value. Now, of course, you don't always have to use the curly braces and the quotes. You just type the name and it works as long as it's a valid Python identifier. Very convenient. And then we can reference it. So when Python sees the a, it says, that's not a literal. It's not a string. It's not an int. But it looks like a name. I'll check. It looks up the name. This time it found it as opposed to last time where it got a name error. This time it finds it. It then throws the name away and just uses the object itself, and then that object, because its value is it's the object which represents 300, prints out the value, right? So there's how we add a name to a namespace or overwrite what the name has or what it refers to. Okay, b equals a is saying whatever a refers to, I want b to be another name for it. So I've created a second name for the object that a referred to already. Okay, so again, I'm going slow to make you think about it that way. Cool. And because they are both names for the same object, the IDs of the two is the same. So you can say A is B. It says, is the object that A refers to, the name A refers to an object, the name B refers to an object. Do they refer to the same object? Is will tell you if that's true or false. In this case, it's true. Del A is the way you remove a name from a namespace. Right? It's not the way you delete an object, because that object might not be deleted. There might be some other name referring to it, or the garbage collector might decide it's busy right now or doesn't want to run right now. So del, the equal sign or assignment, and the del are the first two examples we're going to see of a namespace operation. They are changing the namespace. Right? So you think of del, you think, oh, it's deleting the object. No, it's deleting the name. And the name referred to an object, and the object still might be there. Okay? All right. Attributes, similar, right? So I can have a my namespace dictionary. Think about the way you do attribute access. So I could do that and sort of show you that I've got R and X. Right? In the types, after 3.3, there's a simple namespace, which is sort of like the class with a pass that you often see in before Python 3.3. So this is the way you would do it if you were doing a dictionary. In a namespace, attributes of an object, it looks like this, right? So this is the way you do sort of nested namespaces. So is checks identity not equality? Right? Okay? Is checks identity. Is the object that I refers to and the object that J refers to, are they the same object? Not necessarily. I created them separately. In this case, Python decided to create them as separate objects. Okay? So don't use is unless you really mean is. You really mean I want to know, is this name and that name, do they refer to the same object? Okay? And in case you're curious why that's different, it's because Python pre-creates, CPython, this version, pre-creates integer objects from, I think, -5 to 2.
256, and then we start to see different addresses. So if you want to poke around and see, you can figure out, oh, that's approximately how many. Or you can go read the C code, which is probably easier. Okay, some exercises for you to do relative to names. Remember, type what you see, think about what it's going to do, and then hit enter to see if you got it right. So while I'm rocking around, you can turn this off. Bored yet? I'm always nervous at the beginning, and some people are going to walk out because I'm going so slow. It gets faster. Laying the foundation. No. Bring some work or leave. No, not a lot. A little bit, but I'm trying to think which parts of the. I mean, people do get confused on purpose, but I usually explain it afterwards. So. Okay, I'm going to move you along now. How many of you finished the exercises? How many got halfway through? Okay, that helps me to gauge if I'm moving us too fast or too slow. So again, I'm trying to move on when 10% of the people are done. That's about ideal for me, I think, in terms of when we'll keep moving.
And then you'll have to go back and do some of them later. And I'm going to explain most of them here. So, any surprises here? This is where if it doesn't make sense, I'll just go through it slowly. If I think you probably all got it. If you didn't, raise your hand or shout out, and I will slow down and explain what's going on. Those are all fairly straightforward, I think. Now that should not have been a surprise to anyone, that because M and N refer to the same list, then if I change the list, which M refers to, the list, which N refers to, it's the same list, it changed, right? No surprise. So here you can see that, yep, they are the same. The S and T both refer to the same object, and they have the same ID. Now this one, on the other hand, might be confusing to some of you. A few of you, I think, maybe a third of you might go, what? So what's going on here is that what happened is S and T both refer to this object, which is the string hello. Right here what happened is Python said, okay, let me create a new string object, space there. Let me go get the string object that S refers to, which is hello. Let me construct with the plus, hello space there, a new object, hello space there, and let me make S refer to that new object. It didn't change T, because T is no longer, T is referring to the old. Okay, so that's what's going on there and why that looks a little, it looks a little different. And we're going to explore that a little bit more, why list and string seem to act differently. Well, they do act differently, really. Okay, this one is similar, but it's actually using the plus equal just like I did with the string. And you can see that plus equal works the same as equal plus up there. No surprise. Int add. It's not, okay, great, that's good to know. I can't change the add. So int dunder add, int.dunder add is a name which refers to the an object, which refers to a method on the int class that is the same as what gets invoked when you call, 3 plus 9, for example, the plus operator. And you can't change built-in ones, that's reassuring. Here I was just exploring what happens if you call the object built-in type and create a new instance of it. What creates this new object? There's a built-in none object. Oh, I just gave it away. Like, what is none? It's a name. You get to use it. It's not null or nil. It's an object. It's just an object that at the beginning of Python interpreter time, we said, oh, there's the name none. And if you want to access it, here's its name. And you can use that for your own. So if you actually look at the difference between none and the new object, about the only difference in terms of attributes is the dunder bool. Digress for a moment, and here's a get ref count. You want to know how many names refer to an object in Python? You can ask it, and nearly 6,000 names in the Python that I've got running here refer to none. How big was that for you, by the way? Quite a bit smaller, I think, because I'm running an interpreter inside an interpreter. Maybe half that. How much? 1,500. Okay, so so I've got quite a bit more because I'm running, like I said, I'm running an interpreter inside an interpreter, so I can use this. So I could say, what are the refs of the built-in type object? Refs of new object, there's only 2 there, right? And one of them actually is in refs, and the other is new object name itself. So if I ever need a sentinel in Python, something that I know I'm not going to see on the input file, or something that when this one arrives, it's like out-of-band data. You can do it like this. Just create an object, and now you've got your own private none, sort of. It's your own, whatever you need to use it for. So that's handy occasionally. It's only going to be true when compared to itself. How many refs are there for, how many references are there for the various built-in? You can see with already 2,000 names that refer to the built-in, which refer to the pre-created instance of int, which represents the integer 1, it makes sense that it was pre-allocated, right? It speeds up startup time and other things. And it sort of tails off. If you're curious how it tails off, I was. So I'm like, oh, okay, how many are there? It looks like it's, they could have stopped around here and gotten most of the gain from that for a script that does not very much. Anyway, okay, so namespaces. Let me talk a little bit more formally about namespaces now. Any questions before I move on? There we go. Oh, yeah. So a namespace is a mapping from a valid from a valid identifier name to an object. Assignment is a namespace operation. It's not an operation on objects. It's not an operation on what I would say. I would avoid the use of the word variable if that has been confusing to you. A scope is a section of code where a namespace is directly accessible. I just keep losing focus. So for directly accessible namespaces, you access it just by using the name. For indirectly ones, you use a dot notation. Nothing new here. Those are some examples like sys.version until. Here's the direct namespace search order from the Python tutorial. First, it looks at local names. Then it looks in enclosing functions going out. Then it looks at the current module's global names. And finally, it looks at the built-in names. So it does a search on its way out for finding a name. All namespace changes happen in the local scope, right? In the current scope being executed for whatever namespace operation it is. And here are the main namespace operations. Equal sign we saw, del I mentioned, import, def, and class are the three other big ones. And then there's a few minor ones, like a function parameter gets bound to an object. That's a namespace operation when the function gets called. For loop, you can have a new name there. Exception as, you can have a new name that gets created. With, new name gets created. And actually, I stumbled across this last week when I was given a dry run for this. I realized, oh, right, dunder doc gets created just by the presence of a string at certain locations. And there may be others. If you find them, let me know. I'll add them to the list. Just in case you're curious, what are all the ways that namespaces can change? Okay, so let's look at some code. Len is a built-in function. Don't do this. In general, if there's a built-in name, stay away from it, unless there's a really good reason. I can't think of one. I've never seen a good reason. Use something else. Use an underscore in front of it or change its name. But here what I've done is I've defined a function f1. In that function, I've defined a function len. In that function, inner function, I've defined a new local variable len. And then I print some stuff out, and then I actually return a call. I call that inner function len and return it, right? So if I call f1, we're going to see that in f1, len equals, and it's referring to, oh, sorry, here. This one executes right here. In f1 at this point, what is len? Len refers to this function. And it's got a nice name, eh? They've cleaned this up quite a bit with newer versions of Python. So it's function f1 locals. So it's in the function f1, there are some locals, and there's a len, which is a local function. So that's very nice. And then when we call that one, we call that, and in here, len refers to the range 3, and then we return. Let's change this slightly just by commenting out that one line. And now when we call it, we can see, oh, you know, again, you don't have to understand the details. The point is you can see it's going to look at the names according to the rules that I mentioned earlier. Okay? Of course, len, still a built-in function because all those namespace changes happened in the scope where they were executing. So it didn't change the built-in name that we get back to once we're back out of those functions. You can do that if you want. Right? So len is not a keyword in Python. It's only a built-in, and you can override it with whatever you want. And then I could have a function that tries to call it, and if you pass it a string and it should return 4, it instead says, I'm sorry, I can't call 99, right? Because in here, it's going to look locally, can't find it, goes out to the global scope and finds, oh, there's a name, and it refers to the integer 99, right? There it is. Now if I del len, what does that do? Is len now unavailable to me? No, I've just replaced the global name, and the built-in name is now exposed again. Okay, so that's some bad code to show you how you can get confused if you're not careful with using built-in names, and just help you think about how the name resolution happens and how namespace changes, where they happen and what they apply to, what scope they apply to. Right, and now that works again. Phew. Of course, pass. If I say pass equal 3, is that going to do anything? No, because it's a syntax error. So there are some things that are syntax errors, others that are not. A good, one of the reasons that pass gives you a syntax error and len doesn't is len's a built-in, pass is a keyword. The other thing is, does pass exist at runtime? But does it represent something that exists at runtime? Len does. Len, in your code, you see len, at runtime, it's going to refer to an object. Pass in your code I haven't checked the bytecode. I don't know if there's a no-op in the bytecode for Python, but I suspect it doesn't ever exist in that sense. So what you said is totally right. I was thinking of the other sense. And same thing with del, right? Del's a syntax error. And well, del is a keyword, so it always has to have something after it. So what are all the keywords? They are these, which we're not going to look at in depth, but some of them, like false, is now a keyword in newer versions of the language, and a bunch of others that are kind of interesting. It's kind of interesting which ones are keywords and which ones aren't. It sort of helps you understand what's going on behind the scenes, but not really necessary to know. So function locals we talked about. Some of you have seen this and go, oh yeah, I've seen that. If you haven't seen this, or some of you have seen this and say, oh yeah, that happened, and when I first saw it, I was so confused. And if you haven't seen it yet, I'll confuse you now so you won't be confused later. So, x equal 1. So if I call test1, it's going to print, it's going to find that x, it's going to print 1, and what about this one? So I've defined that function test2. In the function, I'm going to create a new name x, bind it to a new object, the 2, print it. Okay, so it's 1 before I start the function. There is an x at the at that current scope, which refers to the object int1. Inside there, I got a new name, gave it a value, as in made it bound it to an object, and then displayed it, and we get back x is 1. No surprise. This is all simple stuff, right? Okay. How about this one? X 1. Oh, yeah. Oh, right. Yeah. So yeah, there's that weirdness, right? So what's going on here? What's going on is Python, when Python sees the def, it compiles a code object. It parses that function and creates a code object that it's going to execute later. As it's going through, it says, I see an assignment to a name x. That must be a local variable. I will keep track of the fact that I need a local variable in this function, and its name is x. Then, when I execute the function, it tries to access the local variable x because it knows that in this function, x is local, and it can't. And so it says, there is a local variable x which was referenced before assignment. That's right, there's the local variable x, and it was referenced before assignment. So in other words, what the other thing Python, I suppose, could have done would be to say, well, at this point, x refers to the outer scope, and only starting here, that's not the way Python compiles. Okay, so that's, if you see that error, that's what's going on, right? And of course, x is still 1. So here's how we can actually go poke around and see some of this. So there's the code for test 3. Well, you can't see the code there, but it's in there. You can use the dis module to disassemble it if you want to actually see the bytecode that got created. The code has a whole bunch of interesting, the dunder code attribute has a bunch of interesting attributes hung off it, such as the argument count. Test 3 takes no arguments. Its name, right? So the name test 3, when we do a def of test 3, the test3, those 5 characters go at least 2 places. One, they went into the current namespace. The other, they went into the code object, which is what the test 3 refers to. Okay, that's an important thing to remember, especially for later. Names, so it used some names internally, like print. It's got 1 local, and the local variable names are just the 1, x, right? So it knows that's a local name. Okay? Here's from the tutorial exactly why this fails, right? Right, so that explains, there's the authoritative answer, or an authoritative answer to say, here's why you can't do what we tried to do, and it gave us that weird unbound local error. So what does this do? Well, global, one of those keywords, is, it basically says, Python, when you're compiling this, please don't make a local for this one. Use the one from the outer scope instead. Okay? So x beforehand is 1. When we call, it's going to show it as 1 because it gets it from the outer, the enclosing namespace. Then it is going to change what x, the only x. There's only one name. In this code, there's only the name before we call it, and inside it's the same name. The name that's inside the function is going to refer to the same object. Sorry. the name inside is, it's the same name. It's not just that the names are the same, X and X. If I change that, no, that wouldn't have worked. So you can see that afterwards it actually changed the global X, the one that was outside. Okay? And you can see here, test 4 has no local variables because the global said, nope, when you compile it, don't make a new local variable. In Python 3, I think it was 3.0, where non-local was added. Non-local is something between default behavior and global. It says, well, don't go all the way to global, just go as far as you need to. Okay? So in this case, what's going to happen is non-local X, Python is, that tells Python, don't create a local X to this test 6 code. Go out until you find an X. And here it found it here. It didn't have to go all the way to local, to globals, sorry. So it found it here. And so now if we call it, X is 1 to start with. Oh, let's make it 1 to start with because it was 4. And now when we call test 5, it's going to show us, it's going to define this function. X is assigned to 5. It's going to show us that it's 5. It's going to call it, make it 6 and show us it's 6. Afterwards, it's going to show up as 6 because non-local refers to that X. Phew, got it right. But what is X at this point? It wasn't global X, it was non-local X. So it's going to stay what it was in the global namespace. Okay, so that's how non-local works. Same as global, just not quite as aggressive. Okay. So a couple more things here. So if you read that, sorry, the formatting is not ideal, but the attributes, that's because I try to make a big font so even the people in the back can see. If you read that, there are a few weasel words in there. It doesn't say these are the attributes of the object. It says these are the attributes that may be reachable from the object, etc. So let's look at what's in the current namespace. Current scope, it's the global. So I'm going to import some stuff and make a few, grab a bound method here and create a little function for myself and blah, blah, blah. I just want to explore the current namespace, and you can go look at that code later if you're interested to see how it works. So all the names in the current namespace that don't start with an underscore, there are 141 built-ins that you have access to when you fire up Python. Some of them are exceptions, specifically 64 of them. Okay, so there's 64 exceptions that are built-ins that you get, and there they all are. And here's a nicer list of them that shows you. And this is quite a few more than if you're running Python 2.7. In Python 3, the exception hierarchy was made richer in quite a few good ways. Like you can see under OS error, there's lots of variety. So a lot of code that used to say, well, if it was an OS error and it was this specific type of OS error, now you can just use a more precise exception. So there's the full exception hierarchy from the documentation. Hang on. So those are all the exceptions, and that's where you can find them. There are 77 left, and here they all are. There's all the stuff. And let's look at these briefly. So if I look at the type of what the int refers to, it's a class type, and len is a built-in function. Well, a whole bunch of these are either type or built-in functions. Specifically, all of these are types. Interesting that zip is a type, and range is a type, and reversed is a type. And it's just, these are implementation details. That's the main thing to take away from why would that be a type? Well, because it made more sense to implement it that way. And all of these ones are classes. Okay? And then the only thing left is there's ellipses, none, some exit and quit, false and true, help, copyrights, and not implemented, right? So that's sort of all the things in built-ins, the kinds of things you have access to. So your turn to do some more exercises now. Interesting. Okay, so this was a short exercise just to give you a chance to, well, be a chance to stop talking, you a chance to stop listening to me. Locals and globals are functions that return, in this case, they're the same because I'm at the global scope level, that return dictionary-like objects. And you notice I said dictionary-like objects. They're not exactly the same as dictionaries, or at least they don't act like it in the context of some other places. So you could do this. You could try to access X in the current namespace, can't get it, or you can access the current namespace as a dictionary and try to get it. You can't get it, but you could add it, and then it's there. Right? Don't do this. It's a bad thing, but you could. And I will admit that I have, and part of why it's a bad idea is fast locals. There are cases where you can easily break this and use that, and then X doesn't show up because of some optimizations behind the scenes. The one time I thought I had an example. I may have dropped it by mistake. The one time I have used this is hack throwaway script. I just need to do some printing, and I don't want to put all the names in. I just pass star locals to the format operator. But don't tell anyone I've actually done that. So namespace changes. Any questions on any of that? So assignment, globals and locals, but don't use them. Import, def, class, del, and of course those ones. Let's go look at import and see how it works. It's fairly straightforward, but there are a couple things about it that are maybe surprising, or you might not have realized they're sort of funny, like your comment. They're actually kind of confusing. Well, not confusing, but they're interesting. So import preprint, what that does is changes the current namespace, so it has a new name in it, which is pprint, the pretty print module. And pprint is now a name in my current namespace that refers to the object, which is that module that just got imported. And it's got, there's the module, and there's where it got it. And it's got a bunch of attributes in it, right? And the attributes that are just the ones that aren't underscore, starting with underscore. There's pretty print, or is readable, is recursive, p format, pprint, re, and a safe repr. Okay? Interesting, exposes re through there. I can access the p format function that's in the pprint module. I can access the pprint function that's in the pprint module. I kind of have a love-hate relationship with modules that expose one of their primary interfaces as the same name. Sorry. There is no access, there's no .foo in the pprint module, right? Okay. Oh, now there is. You can do that, right? Python lets you do this lots of places. You can add attributes to functions. You can add them to modules that aren't yours, some modules at least. So in certain cases, that's really handy and really useful. Not generally a good idea to add module attributes. I can't think of a good use case for it. Someone probably has, though. So here I can say, go look, find the pprint module. Inside it, grab the pformat attribute and pull it into my current namespace as pprint underscore pformat. That's what I'm telling Python to do. And so now I can see the pprint underscore pformat is in my current namespace. And it is the same. Those two names refer to the same object, right? So I can get at them two ways now. Okay. So let's get rid of the pprint name in my current namespace. Did that delete the pprint module? No. Del is a namespace operation, right? So I can still access the other stuff. Now let me re-import it as pprint underscore module. Oh, now I've got that name and that name. And they're the same. The p format there is the same, right? So I've changed the name we're referring it to. Now I'm calling it the pprint underscore module. So maybe I want to import a module, but I don't know its name when I'm writing the code. But then at some point later, I store that name, make the name, module name, refer to string. You see I trip over my own words. I use variable language, and I'm trying to avoid that, at least for this tutorial. So module name is string. I can import the import lib, and import lib has an import module function that if you pass it an object, which is a string, in this case, maybe a bad choice, the string, it will try to go look for the string module, and it will import it. And what that function returns is the module object. And I can take that module object and give it a new name in my current namespace, which is string underscore module. Okay? And now I can access it just like I did an import. So basically, this is how you could do, that's the recommended way to do a fairly simple import of a module where you don't know at compile time what its name is, right? And I can access that string module's attributes like that, okay? Did it create string as a name in my current namespace? I didn't tell it to. So, can I import string this way? What's going on there? So, import doesn't look at the contents or the object that name refers to. Import looks at that as a string, right? So, this is also invalid. What's going on here? Well, the answer is, and this is just sort of to close the loop, when you do an import, you give it a Python identifier. It turns it into a string, goes and uses that string to find the module, compiles it, does whatever it needs to, or find that it's already imported, and then returns the module object, and then creates a new name in the local namespace with the identifier, not the string, right? So there's that weird thing that is going on with import that you probably didn't realize maybe exactly like that until now. So when you say import string, that's what it's doing. It's doing two things with that name. It's going to find it, and that's making a new name locally, unless you do from some of the other kinds of things. Any questions on that? So let's look at a few more changes with namespaces. I've got a file structure in my current directory that looks like this. Folder 1 has a file 1. Module 1 has a zero-length dundernet.py, and it has a file 1.py in it, and it's got an attribute 1. So if I, by the way, if you're running Python less than 3.3, this will fail because there's no dunder init in that subdirectory. What's more interesting to me, probably not to you, is that I don't understand why this works in Python 3.3 and greater. Like I thought I understood enough about packages and modules, and I went and looked and read it a couple times a week or two ago. I'm like, I still don't get why this is working. So there's something funny going on in my understanding of the difference between packages and modules and regular ones versus, I can't remember the other name. Anyway, but if I look at folder 1, I did the import, and there's not much in there, eh? I mean, it tells me path and things like that, but there's nothing in there. It does have that path folder, which tells me it's a certain kind of package, or it tells me it's a package. I can import folder 1.file1, and now I can see that it got imported, and it's got that attribute 1. If I import module 1, it works even in Python 2.7 and 3.2 and before. I can't remember when 3.2, it's right there. So 3.2 and before, this one will always work because there's the dunder init file, zero length, even if it's empty, that gets imported, that exists there. Then you can import and give the name of a directory. It sees that the dunder init.py file exists in that directory, and it lets you import the directory as a package. Right, so now I've got module 1. Okay, and I can import module 1.file1, and it'll pull in the specific contents of that one, and I can see it's in folder, oh no, it's not there, but it's under here, right? So if I look at module 1, it's got file 1, and of course, module 1 file 1 has the attribute 1 in that file as well. Right. From module 1, import file 1 works. Okay, so I'm not going to talk a lot about I'm not going to talk any more about packages or modules or what you do in dundernet. That's not in this talk, in this tutorial. Just wanted to explore a little bit of that. I'm focusing on namespace operations. So your turn to go try a few imports and see if you understand how they're working. Okay, let's move. Okay, let's move along. This one's fairly simple as well. Just a couple imports. You can see some of these attributes and what they refer to. From pprint import star, not recommended for code that's going to live a long time and lots of people have to maintain, but useful sometimes. You can actually, if you're writing a module, control what happens when you do that via the dunder all attribute. Import lib, reload, if you're familiar with it in 2.7, has moved in Python 3 to the reload, the import lib module. So if I do an import lib reload CSV, oh, doesn't work because it sees that as a name, can't find it, right? When you do an import space CSV, it figures out how to go find it. But here, it's not going to do that. So that's special magic that the import statement does. So let's try this instead. Well, no, that's not going to work. So reload in Python 2, 7, and 3, it wants a module object as its only argument, right? So let's import CSV, and then we'll try it again. CSV is still not a module object, it's a string, right? So we pass it the object itself. So here CSV refers now to a module object, and now we can ask import lib's reload function, please go check it on the disk and pull it in again, okay? Sys.path, this is how it goes and looks for things. Functions, any questions on imports? Again, I'm focusing on the namespace end of how imports work. So let's define a function. Functions have some attributes. You can give them new ones if you want. It has one called dunder name, and you can see what happened here. Remember, I mentioned this before. F, that name F went into two places. It went into my local namespace, and it went in, which shows up here, and it went into the dunder name attribute of the function object that got created, right? So I can change its name like this. And now you can see that the name in my local namespace hasn't changed, but the name of the function object has changed to G. So now if I look at it, it's G, and if I just type F, if you're running Python 2.7, you will see function G. If you're running Python 3.3, 4 at least, I can't remember exactly when it changed, you still see function F. And that's because there's now, there it is, 3.3. There's now a dunder qual name attribute which gets used instead. So if I change qual name in 3.3 and above to G, then when I just look at F and it gives me the repr of it, I get the function G instead. Okay, so that's interesting, very handy if you're doing closures or decorators or anything that's actually creating a new function on the fly. Sometimes you really want to give it a nice name for the users of it. Functions have this dictionary, and that's where it stores attributes when you create a new attribute on the fly for a function that exists. Let's look at argument passing a little bit. Here we're just going to have some regular positional arguments, some keyword or named arguments, and then collect all the rest that might be passed to it and just show them. So you can see there's a dunder defaults that shows us what those are, kind of interesting. I can pass it the 1 and the 2, and it gets default values for K1 and K2. I can, if I want, give names. I can use the named parameters A and B, or I can use the named parameters B and A, kind of convenient if I want to change the order, right? So I've given the positional arguments backwards, but now B is 1 and A is 2, so kind of handy. Yep, so I overrode K1 is now 3, K1 is still K1, K2 is now 4. Well, there are some constraints, of course, right? If you have 2 positional arguments that are required, you got to give them either by position or by name. If not, it's going to complain. And then all the extras get pulled into args and keyword args, any ones you pass along after that. And there's all of them. Okay, so just a quick, for some of you, review. For some of you, oh, those are all some of the things you can do with with keyword arguments and positional arguments. In Python 3, there's some new syntax, I can't remember what version, which is you can have required keyword argument, I think is the correct term for that. It has no defaults, but it has some keyword defaults, all right? And the nice thing about that is, of course, these are not surprising, right? So if I defaults to none. So here I can say C equal true. I can pass it. And I think I hope I have an example. This is new stuff I added a month ago. So here's a default none. Keyword defaults. A default none. And here's the default there. True. And darn, I don't have the example that I thought I put in here, which is I don't think any of these show as well as they should the power of the B equal true. I apologize. So your chance to do some exercises, real quick one with functions and explore how the argument passing works. Okay, let's move along here. So again, simple little examples that you tried. And here's a tuple in a dictionary. And if you haven't seen this, expect a few of you haven't seen this yet or really played with it much, but these are really nice. The star T, which says, please take the contents of whatever T refers to and unpack that sequence and send them as separate parameters to the function. And similarly, the star star D says, take that dictionary and for the key value pairs, make it as though I called key equal value as the function parameters, sort of like this. Okay? And you can do both, of course. And it doesn't have to be a tuple. It can be any kind of sequence that gets turned into a tuple. Tuples show up in lots of places in Python you might not realize. And here's one example where when you call functions, tuples are thrown around. Locals, lots of stuff in mine, not as many in yours. So there's the example I mentioned earlier, the case, the one time I have used locals, just kind of handy if I'm just doing some real quick dirty thing that I'm never going to use again. Kind of fun. And then this is kind of, oh, wait, is that Python syntax? Turns out in Python 3 it is. Function annotations. Anyone here used function annotations? For what? What? Okay. Yep. Okay. So one of the new features in Python that people are pretty excited about because they let you do lots of things. And again, as with most Python additions, they were designed, my impression is designed in a way to be as agnostic as possible. Like we have no clue what people are going to use this for, so let's make sure it's really general, or at least general enough that they can, use it for whatever. So there it is, how they get used.
I'm sorry, can you give an example why you want?
Some of the use cases are types. So if you want to add type checking in Python, you could do it like this. Like the fact you could say, okay, I want D is the fourth parameter and it has to be of type list. Well, then in this code, I could actually access D and say, oh, it must be an instance of list, for example. That would be an example of type checking. Others, anyone else? PyPy, how does it use them? Ah, okay. So I think that is probably the primary use case. I'm not sure. Anyone use traits? Does it? Like I did stuff. I used it long enough ago that when annotations came out, I thought to myself, I wonder if traits is going to start using annotations, but I don't remember if that is a meaningful question or not. I don't remember enough about how traits is implemented in terms of how it does stuff. But traits does validation on parameters. Would be another example. You might validate parameters based on something. Okay, lists are immutable and strings are not mutable. So let's look at some interesting code here. Very similar to what we saw earlier. Right? No surprises there. We saw that. Same thing. No surprises. Right? So remember what's going on here is that S1 used to refer to hello. So I take hello plus there, create a new hello there object, and then S1 now refers to that new object, hello there. Okay, let's do lists. Here's an M1, M2. Right, same as strings. I get the first name refers to a different list than the second list, just like I did with strings. But if I use plus equal here instead of plus, here I use plus equal instead of plus, I got the same thing. Here, if I use plus equal instead of plus, I get something different. Weird. It's because in Python, plus equal is an operator. It's not just equal and plus. It's not just syntactic sugar. Okay? I'll prove it to you. So let's do a compile of that code and then disassemble it to see the bytecode. And you can see the bytecode that gets called in this case is an in-place underscore add. Right? And if I do the same with the s plus equal, m plus equal, s plus equal, I also get an in-place underscore add. Okay? So that's the bytecode saying this is what I want to do to whatever that object happens to have in it, or that name happens to refer to, whatever that object happens to be. So if I take m equals 1, 2, 3, and then okay, so this is what's going on, is the in-place add calls the list object's iadd method, passing it the new list 4. Sorry, it scrolled off. And when I call that, I got a list back. So in-place add returns, it takes an argument, that method does something, it returns the value of what it did, let's say, right? And it changed m too, okay? If I call s1.iadd, what's it going to do? Yeah, there's no iadd on string. Well, but there was an in-place add bytecode. What's going on? Well, the answer is, what's going on is that Python says, oh, well, let me go check and see if there's a, sorry, let me get the right set of slides here. All right, so the difference is that, this is not accurate, I'm sorry, I forgot to correct this piece. str.iadd doesn't exist, but here's, so ignore that one, didn't get that typo fixed, and here's how it actually works. Right? So these methods should attempt to do the operation in place, modifying self, which is what the m in place add bytecode did. and return the result, which is what it did as well. If the specific method is not defined, the augmented assignment falls back to the normal methods. So because there is no iadd attribute or method on the string built-in type, then it fell back and did the plus space equal instead, the s equal s plus. Okay? Is that clear? And that's the language definition, right? Is plus equal is supposed to try to modify it in place. Strings you can't modify in place because they're immutable objects. You can't change them. You can only create new ones and have new names that refer to the new ones. You can't actually change one string and have it become a different string. Similar, very similar. Here's a tuple with items 1 and 2 in it. Let's try adding 1 to the first one, which should give us a tuple of 2, 2. Oh, well, tuple object does not support item assignment. Right, okay, so I should have known better. Let's, in fact, there's the same error, right? I can't change it. This is, oh, darn, another typo, second one. This was supposed to be T1, and you would say that the error is the same. Type object does not support, tuple object does not support item assignment. What about this? That's what comes from making changes last minute and not testing them thoroughly. So if I say that T2 is a list of a tuple of a single element, and I try this, I should get tuple object does not support item assignment. Good. Phew. We're happy. Except it actually did something, right? Yeah, it's a little Python wart. But think about it, what it's doing, and you'll understand. Like, let's go back. T2 equals that. There it is. iadd called on this. That method called on that object, the list with just the list with just one string in it. What it's supposed to do is try to modify that in place by appending a new element to it, or actually, sorry, appending a new list to itself. And so it's going to give us, it's going to make the change. It's going to return. It's both going to make the change to that list. So it's now going to be the word 1 and the word 2, and it's going to return it. Cool. And if we look at the result, there it is. And if we look at that value, there it is. Right? The problem is, after it did all that, then it tried to make the tuple assignment, and that's when it got the error. Okay, so if you ever wondered why that wart acts the way it does, that's why. Because it's when it tries to do this is when that error comes up. But that was after all that other stuff happened. Okay? Okay. Parameters by reference. So now that we understand all that, here's a quick example to help you think clearly about how does Python pass parameters. And a few of you might have thought, you know, yeah, is it passed by reference or passed by value or something else? And here's sort of a simple case that shows you how it seems to be confusing, right? So str is a name that refers to the object hello. So s here is going to refer to the object, which is the string hello. So what's this going to do? Right, so there was before, and here it's after. But when I look at str2 at the global level, it's still going to be hello, right? And if you're in doubt, it's the test1 function. When we call that function this way, it's exactly the same as if we call it this way, right? Python sees the str2 and substitutes, in a sense, the string hello, and then passes it off. So of course it has to, because when you see it this way, it might be more obvious that it can't change the string hello. Strings are immutable, right? Whereas if you do this, what's going to happen? Well, because lists are mutable, then of course that works. But when we look at list 3, it was mutated. It was changed, right? Because plus equal in place add mutated the list. Okay. The break is when? Is it starting right now? Perfect time. Then let's have our 20-minute break. 1:20, 2:20. Is it now or in 10 minutes? Okay. Well, let's go a little further then. So the break's in 10 minutes. Nice try. I know you're kind of need a break. At least I think you might. So let's do a few things with decorators. This should be a good way to finish and thoroughly confuse you. No, that's not true. Give you some interesting things. So what does a decorator do? Is anybody here scared of decorators? Mystery a little bit? Maybe a few of you? Moderately mystified. Okay. I will not help you. So this might hurt your brain, but I think you'll also go, oh, the mechanics of it are really simple. And once you've gotten that part down, then I think you won't be scared of them if you are, and it'll make more sense how you might use them, or existing ones, or write your own. So basically, I would say a decorator modifies an existing function. It modifies is not really quite accurate, but the point is that it gives you something new that behaves differently. And it either does that before that function starts executing, possibly changing parameters that get passed to it, or after it's done executing, possibly changing what gets returned from it. That's at an abstract level, I'd say, what decorators do. And this is actually a brand new slide, a couple weeks old. So if you have feedback on that, I'd love to hear it, because I'm not sure I think I'm pretty happy with it. Sorry. So all right, let's look at some simple code. Square, brand new function, returns the square of a number. Woohoo, exciting. Let's create a function called trace function, which takes as a parameter a function f. And what it does is it defines a new function and returns that new function. Okay, so this is a function, you pass it a function, it gives you back a new function. The new function it's going to give you is one that takes any number of arguments. It then prints that it got called, and then it actually calls this function, which wasn't passed to it, but was passed to here, right? So basically, when this thing gets compiled, it goes and finds that f and uses it. Then it calls that function, passing whatever args, and then it just tells you that it's returned the result. It actually returns the result. So the function that this thing returns does all this. So let's use it. So if we say trace function, pass it the square function, and we get this traced square is the new name for the object that I just created. So this function returned a new object, which is basically this function, and that new object is going to have this name. And in that object, there is a reference to an f, which was passed into trace function, which is going to be the function square. Okay? So now if we say traced square, oh, there we go. It called square, and it said returning, then it actually called it, and then it actually returned, it says it's going to return 4, and then it actually returned 4, and we see the 4 printed. Simple enough. Okay. So here's how a decorator works, is you, instead of saying trace square equals trace function square, let's create a new function cube and call trace function on it by putting the @trace function in front of it. Okay? So what that does is Python looks at this definition, and what does it do with the name cube? It does two things, right? It goes and creates a new function object and puts that name in that function object. Then it takes that function object and passes it off to the trace function. And what the trace function returns, Python takes the name cube and creates a new name in the current namespace, which refers to whatever that function returned. Right? So that's the key. That's all that decorators do. So if I call cube2, oh, look, there it is, called cube2, returning 8, 8, right? All works. The exercise you're going to do shortly will, if you still didn't get it, I think it might help you get it in a weird way. So memoize, common use case, right? So I've got, basically I create a cache in here. I check to see if I've already been called with those arguments and return the value that was computed the last time. If not, I call the function that I'm trying to memoize, which itself we assume is really computationally intensive and takes a long time, so I don't ever want to call it twice because it always returns the same value given the arguments. And then I'm going to, print some of this stuff out. So if I memoize cube3, if I memorize cube, memoize cube, then when I call cube2, computes 8, computes 27. This time it should give me a hit. Woo, got a hit. So there's sort of one of the standard use cases for a decorator that modifies the behavior of this function. And this time it's modifying it by catching the arguments and then not even calling the function it was supposed to call because, oh, you've called me before with these arguments. I've already got the answer. I'll just give you the answer I computed last time. Okay. So about 5 minutes until the break. the exercise, sorry. So go ahead and do the exercise. And it's kind of a confusing one, but on purpose. And I think it might help you understand decorators and not be scared, because it boils it down to just the mechanics of it if you get it. But feel free to take a break. So we'll stop now for a 25-minute break instead of a 20-minute break. And sometime in those 25 minutes, spend 5 minutes doing the exercise. Okay? So I'll go through it. Yes. Oh, it is a long exercise. Yeah, okay. Lots of stuff to do in this exercise. Sorry, do you want more time? How many people are done? How many people are half done? Okay, we'll keep going. Because I'm going to show you what you missed anyway, if you didn't finish. Okay, so let's make sure X is not in the current namespace. Nope, it's not there. Return, here's a function. Again, I'm going to go real slow. Some of you, it's too slow, but for some of you, maybe this will make it sink in. So return 3 is a function that always returns 3, no matter what you pass it. What a decorator does is it evaluates the code. It sees the def X and evaluates the code and creates a new function object. Right? And then it takes that function and passes it to the function return 3. And that function, whatever that function returns, is what actually gets stuck into the current namespace as X. Right? So here's a, I was going to use names that I tell my kids not to use, like stupid and idiotic. This is a silly, yeah, I can use that one. This is a silly way to use a decorator, but if you get this, that's how simple the mechanics of decorators are, right? Is it's just going to take that, whatever this thing returns, which usually takes advantage of F, wraps it somehow, or does something before it's called or after it's called, or mucks with its parameters or mucks with its return value. But in this case, it just ignores all that and says, no, just make it 3 all the time, right? So if you understand that, then you understand the namespace operation part of decorators, which in the hall we were talking about, and I think I can say it right, tell me if I get it wrong, that basically a decorator is a function that gets sort of stuck in between halfway through a namespace operation, where the namespace operation, def, is not only a namespace operation. Def, sorry, this one, the def says define a new function and then take its code and make the name X refer to it. Well, in between those two, it says take that code, run it through that, and whatever it returns, make X refer to it. That's where decorators, mechanically, how they work. Okay.
Where does it come from? Like, what's the CS? Like what? I mean, I get the mechanics of it, and I think I can
Why were decorators added to the language? That is a good question. If I don't know the answer historically, if I had to conjecture, I would say that people were doing things like this, where you have a function. Look, oh, I can pass a function to a function. Like in some languages, you can't do that. In Python, you can. So people started using it for interesting things. And then people started realizing, well, you know, these interesting things kind of have, I mean, some similarities to aspect-oriented, where it's like, well, regardless of the function, there's something I might want to do to this function. And I suspect it's something like that is maybe how it came into the language. But I don't know. There are lots of people here who could tell you, who are involved in the decisions. So ask them. Okay. So again, just to be clear, if we hadn't used the decorator syntax, right, it's as though the function got defined and X refers to it in this case. And this is the piece that never happened when we did the decorator version, because it was sort of on hold there. Then it went and called the decorator. Here, we're going to pass that function to this thing, and whatever it returns, 3, is going to be what X refers to. Right? So this is the non-decorator version of how that one up there worked. Yes?
Could you explain why it returns type int of x? You have type of x between the name class int.
Because 3 is an int.
3 is an int, but x is the function.
No, X was the function. All right? And this gets back exactly to the namespace part, right? And how this is working. So let's get it cleared up. So there's a function. So okay. All right, so what that just did is this function object, whatever that got compiled into is a function object. That function object was passed to this function under the name f. And then whatever f returned is what X is going to refer to after the decorator's done. So now X right here is going to refer to that 3.
And someplace in the system, whether you can find it or not, is still the original x.
So this function object that got created on the fly and temporarily, and then the name disappeared, may or may not exist in the Python objects, world of objects. It probably got cleaned up by now. We don't know. That's not our business. But it may be. I doubt it. Well, I don't know. Again, we don't, we're not supposed to worry about how Python does garbage collection in 99% of the time. More than that. Okay?
So that created a global x object?
It created an X object in this scope, right? That's what, like decorators, so when you do a def cube, like up or above, we did def cube, that creates a name cube in the current namespace that refers to whatever the compilation of that function returned, a function object. In this case, the name X gets created in the current namespace with whatever the return function, return underscore 3 function returned when it was passed the code, the function object. It just so happens that the return 3 ignored what we passed it, which is why this is a really weird example. But it forces you to think just about the mechanics when it works. Okay? And again, this here is the same thing, right? Here we did define the function x, and you can access it via the name, and it shows you that there is a function x, so in this case the name is there, and then we're going to say, okay, now whatever, take that function, pass it to return 3. Return 3 is just going to return the integer 3, and then whatever x used to refer to, forget that, and now have x refer to, it's like a new key in the dictionary, now make x refer to that 3. So the one you've done, x is a name which refers to or references the integer 3, and that's why its type is, oh, missed it, it's not there, but its type is int. Yeah?
So, but if we do create a function, like if we did type the, what you call, return 3, it will return as a function, right?
Nope. I don't think so, unless I misunderstood. So you're saying return underscore 3, you can pass it whatever you want. It will always return an int, specifically the int 3.
So if we create a function that returned the integer, though,
That's what return 3 is. It's a function that returns an integer. So if we created one, then what?
okay, I just created a function called 1 that returned 1, the integer 1.
Yep.
And when I did type 1, it says class function.
Sure, and type return 3 is a class function too, but type of X is not. Type of X is int. Okay? These are great questions. This is hard, right? Some of you are like, oh yeah, I got this already, but some of us, and I say us because when I first ran into decorators, like I'm good at lots of stuff, but that level of thinking is kind of, that slows me down, like walking through molasses. And so for me, it's like, oh, okay, now I get it. Yeah. Yes, that is exact. Could be, yep, that's helpful. Okay, so again, backing up to the, okay, we define the function return 3. We execute the function return 3 now. The function's return 3 just got executed. It got past the X and it returned to 3, right? So that's a great comment, which I will add to my notes to actually put a little print or something in there. Okay? Yes?
Question was raised, kind of curious, is there a way to decorate a function outside the definition? So if you have a function instantiated, can you decorate it at that point, or can it only be decorated at time?
Right there. Right? I'm doing it later. Okay? Cool. Okay. Let's keep going. Or maybe I'll just pause for 20 more seconds to let that sink in to those of you who are like, I think I'm getting it. Okay. So, here's another decorator. Doubler, right? It's going to intervene, kind of. It's going to return a new function, which, again, I explained it as it intervenes when a function gets called. But the truth is, that code is injected as part of the decoration, but it's actually a new code object, a new function that gets executed. In this case, and I've called it new f again here, right? So what this is going to do is if I pass a function to doubler, it's going to return a function which when called with any number of arguments will call that original function and then do a *2, like multiply it by 2, let's say. Okay? So cube n return n cubed, and if I decorate that with doubler, then cube is now going to get put into my current namespace, but it won't be this cube, it'll be this function, which is produced in this function that got executed when that just executed doubler, and it just passed f in here, created new f, and that new f thing is what got stored with the name f cube. So cube now refers to that new f, including the f there, which was the original. So it's got a copy of that original code object. Oh, sorry, go back to your question, front row. That answers your question. Yeah, as long as this decorated function lives, then the object is available because it's accessed there, of course. So when I said we don't know if it's cleaned up or not, we absolutely do know it's not cleaned up. Not yet, not until the cube name goes away. Okay, so cube 1 is going to return 2, right? Because cube 1 got passed to this function, which is that function. 1 times 1 times 1 got returned, and 1 times 2 is 2, all right? Cube 2, same thing happens, right? Here's another example, right? Now, the reason I threw this example in is because here, 2 times, we're thinking ints, right? But typically in Python, we want to be able, people would, whatever we do, what code we write, if we're careful, it can be used later in ways that we didn't imagine that are helpful to others, right? And here would be an example. Not that this is a terribly helpful decorator, but hopefully it helps you understand them. Another example, so in case you haven't seen this before, if you define a class and you define a dunder call method, then instances of that class can be called like a function, right? So self.count, c.count is 0. So if when I call c, this method gets called. Very handy thing. If you have you want a function to have some state, this is a really simple way to do it in many cases, right? So I call that thing, and I call that thing, and now c.count, because every time I call it, all it's going to do is increment, is going to be 2, right? Not terribly useful, but let's make something slightly more complicated, that I've added this, I've added this, I've added this. So I put in 2 print statements. I changed it to class function counter. I remembered the function that we were passed when we were created, and I actually called it, right? So in terms of behavior, if we get rid of the print function and the print function, and we ignore the self.count, this is a function counter class. Well, let me just show you. I think it'll be more clear. So let's define plural, which just returns whatever string you pass it with an S on the end. So if I say, let's create a new instance of the function counter class, passing it this function, I get back an object, an instance of the class function counter, which, you can see that that's actually called. It's got an attribute, self.count, and every time I call this thing, treat it like a function, you might think, to call it, then it's actually going to just return plural. So in its decoration, it's not changing the parameters passed into plural. It's not changing the return value from plural. It's only keeping track of some state and letting me get at it later. It's doing a few prints as well, right? So now if I say plural counter dog, plural counter cat, right? So it's telling me, it's saying, hey, it got called, and it's incrementing count. And now I can say, okay, how many times was plural counter called? And the answer is 2 times. Okay, so there's another little simple use case. You want to trace something or count something. There's the way you do it. But this one's using the dunder call for a count. And you noticed I broke PEP8, right, by calling my class function underscore counter. Well, that's because I'd like to use it like a decorator. And decorators are usually functions, and so I thought maybe it would make more sense to do it that way. Okay? So I started by describing function counter as a function. I said decorators are functions that, blah, 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 blah. No, decorators are callables that, blah, 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 blah. Okay? And like much of Python, lots of ways to do a call. Well, lots of ways to do lots of operations, which is one of the great things about the language. Any questions? If you're still confused, hang out afterwards, and it might be that one more time makes it sink home. Okay. The class statement. 4 slides. Oh, more lecture. So my focus on namespaces again, and we're going to do some behind-the-scenes interesting stuff. I hope it's interesting. So the class statement starts a block of code, creates a new namespace. All the name changes are in that block, right? And it also creates a name for the class in the namespace of the module where it appears. Instances are, the way you create a class is you call it like it's a function. It's sort of, again, it's a callable. So you instantiate that way. Dunder init gets called, and it gets passed the new object that already got created before you got to dunder init, right? And if you need to override how that thing does it, you can do so by changing dunder new. So if you compare, some people call dunder init a constructor, comparing it to languages like C++, and that's a significant difference because it doesn't actually construct the object, it just initializes it. And when you access a method name on a class instance, an instance of the class on the object itself, it returns a method object if it can find method name in the class. Okay. And it binds the class instance, the first parameter. Okay, so here's a class. Number, remembers the amount, add, print some stuff, adds whatever you pass to whatever it knows it is, based on the amount attribute it's keeping in the self. All right? So let's play around with this a little bit. So there's the same function. I think I added a doc string, I added a version, I put in some number signs so it wouldn't confuse the interpreter. All right, class number, yep, cool. Help works. There's my function. Number.dunder init is a function. So is number.add. Oh, bunch of stuff there. Let's just look at the stuff that doesn't start with double underscores. So number has an attribute add. All right, let's create an instance of the class. It's now going to have an amount. You may have to look at your handout to remember that we did self.amount equals whatever we passed it. So now self.amount is 2. So numbers.amount is 2. There, okay. Notice here it says, up here it said function dunderInit and function number.add. Here it's saying bound method number.dunderInit and bound method number.add, right? So this is how Python, this is how object-oriented programming, object-oriented languages are implemented typically. So, oh, that's interesting. What are the attributes of number 2? They are add and amount. But amount, we know it is part of the instance because self.amount that attribute got added and referenced the 2 when dunderInit was called. But the add attribute is not actually an attribute of number 2 at all. It's an attribute of the class of which number 2 is an instance, right? Which is what that slide back there said. If I look at the difference between these, okay, so if I look at all their attributes, the only difference is that number 2 has amount where number didn't, because the attributes, the instance variables or fields of an object, of instances of a class, are what differ. The behavior is all in the class, it's all the same. So typically you will see all these attributes down here contain the differentness between the various objects. Okay, that's where it stores it. There's a dunderdict that on the attribute is where those attributes are stored for instances. Number itself, the class has an attribute as well, which has some of these things and a whole bunch of stuff either there or maybe coming from elsewhere, and it's got the add function in there. Okay, so number2.add, we saw. Here's how you add 3 to the number 2. We saw the call happen, we return 5. All right, so here's where I'm going to start doing some weird things to help you understand. Here's exactly how it's happening behind the scenes. So if I call number.add2, what is number2.add? It's a function. What's that? No, it's a function. It's just a function, right? It's a method defined in a class, but in thinking about the object, yeah, it's going to say, sorry, you need to pass me self and amount. I think were the names of the parameters internal. The point is you need 2 parameters. And we could go look at the func dunder code, the dunder code co-arg count or whatever and prove this, but no, it tells us, sorry, required positional argument value, right? So I could do that, and would that work? Why not? Doesn't matter. Why doesn't this work? I want a better answer. Sorry, I'm being, what? Nope. 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 No. Close. You're getting closer every time. The first parameter has to be an object that has an amount attribute. Duck typing, right? Like just that's the behavior that's required of the add function. The add function takes its first argument, accesses the amount attribute of it, adds it to the second parameter, and returns the value. Right? So all those answers were partly right and getting closer and closer, but I would say the real answer is that that doesn't work because if you call 2.amount, it will fail if you try to access amount on 2. Oh, look at that. See, that's the real reason why it failed. Right? Now, all those other reasons were true too, right? Because we're doing weird things here. But that's really why it failed, is that can't work. If you call the add function that's defined in the number class, that's correct, right? So classes really aren't that magic, eh? What is magic is when you access the method on the instance. That's where the magic comes in, and we'll see that. So does number 2 have a amount attribute? Absolutely. So that will work, right? Yeah, I know. Don't do this. I'm sorry. You're all shaking your heads. Fine. Go ahead, shake your heads. I hope it's helping. I think it does. I think sort of we're looking behind the curtain, right? In the Wizard of Oz. Oh, that's what's actually going on. And then some stuff is less mysterious, or you see weird things. You're like, oh, yeah, I get it. Now I understand how it's wired up. And For some of you, it will be interesting because you are curious in the same way that I'm curious. Others of you, it will be helpful because it will help you understand behind the scenes. And others of you might, well, that was useless, and sorry about that. Hopefully there's good stuff in it somewhere. Okay, so, of course, here's the right way to add it, right? You call the add method on the number 2 object that it refers to, and you pass it a 3, right? And it works. And again, thinking back to the amount and why it failed, like, do we have to pass it an int? No, just have to pass it something that it can do a plus with whatever it was initialized as, right? So we could do some funky stuff with strings in here. And anyway, okay, so let's get a little weirder here. Let's do some monkey patching. Set double amounts. It's just same as done during init, but it's going to double whatever it's passed and store that in the amount attribute. So there's number dot done during init. What's that? Ah, great. Okay, so there's dundernet, number.dundernet is just a function number, and we can do help on it. Let's change it. Let's say, no. Let's make number dundernet be this function instead. All right, there we go. So now if I do number 4 equal number 2, of course, stop shaking your head. Of course, I'm conveniently called it number 4 to give you a hint what's going to happen, right? Oh, excellent, it did it. Cool. If I number 4 add 5 gets 9, everything's working. As long as I remember that I got to give half the number I really want, right? And there's number dot dundernet bound method, number 2 bound method, right? So you can see that both instances, number 2 and number 4, both are accessing this new monkey patched dundernet method, right? Yeah, okay, here's another one. Let's put a multiply by into our class, right? Nothing weird there, it's just a function. But now I'm going to do something that's not right. Give you a little clue there. So number 4.mul, I want to add that as an attribute to the instance. So now I can access it. Oh, is that what we expected? Well, if you're on the ball and you saw my mistake, it is. But if not, you'd say, shouldn't it be a bound method? Number 2.dunderInit is a bound method here. It's a function multiply by. And if I try to call it, it says it's missing one required positional argument value, right? I can call it like that, and it works, but you shouldn't have to call it like that. So something weird happened in this monkey patch, and the answer is, this will help you understand maybe, right? So number 4 has a mul, number 10 does not, because I put the mul on number 4 on the instance instead of on the class, right? And this is getting closer to where's the magic, and the magic is it's when it goes and finds it somewhere else is when it returns a bound method. So if I look at what's on number 10, it's got add and amount. If I look at what's on number, it's only got add, and number 4 has mul, right? So you can see we've got the function, the method defined in the class. We've got the attribute of the instance. There's also dunderInit, which I'm not showing because I'm using this little fake derpy. Number itself only has the method, and then mul is stuck down here and it's being stuck in there. So that's what we should have done, right? Ta-da! It works. Yippee! Oh, I was going to say yippee, and I can't. I've still got an instance on number 4, right? So number 4's dict has a mul, which is a function multiply by, and it's saying, sorry. So what I need to do is get rid of that thing. And now, oh, look, derp of number 4 used to show me add amount and mul. Now it shows me add amount and mul. But now instead of the mole coming from the dictionary, the mole is coming from the superclass, sorry, the class of which number 4 is an instance. And you can see it's in the class. The method is in the class, and when I access it, I get a bound method number multiplied by. Okay? So it's when you access an instance and it can't find the attribute, and it looks in the class or superclasses and finds the attribute, and it's a function that it gives back to you not that function, but a bound method object. That's the magic that's going on behind the scenes. Very simple, really, with Python, object-oriented, and instances. Right? Now everything works. So how does it actually remember all this? Well, here's another way to think about it. Okay, right, so you can see the difference here, function, bound method. So what is a bound method? Well, let's look at what it has. Nothing. Nothing that doesn't start with an underscore. But if we look at the differences there, we see that number 4, so number 4.add is refers to the bound method number. It's the object, which is the bound method. And the bound method, here's how it's different. Here's the function in the class. Here's the method on the object. And you can see that it knows two things that the number doesn't. It's got a dunder self and it's got a dunder func. Right? Its dunder self is the number object, that one. And it is number 4, right? So number 4, basically the bound method remembers what object it's bound to. So there's the binding. That's where it keeps it. Now, why does it need to do that binding now? Or why is it useful to us for it to do that binding when it's actually retrieved? Here's why. I might want a function called add value to number 4 that adds 4 to whatever number it is. So there's my function. It's a bound method, but it works as a function. I can add 4 to 6, and I can add, right? It just works, right? So accessing, if you haven't seen this before, where you access a method on an object and then turn that around and pass it as a function to something else, for example, and just that function can get called, it already knows about the function. So that's a very useful, handy kind of thing. There's an example of it. And then it's got the function. So it knows itself and it knows the func. And the func just refers to the number. The numbers class, then add function. So there's the self, and the add func is that one, yep. So we believe that's actually true. And it's the same function. That makes sense. The function is the same. The bound method is very different because it has a different self, but the function is the same. It just refers to the function defined up in the class. So when we call number 4.add5, it's like we called that, right? So the number 4.add, it's when that attribute gets accessed that the bound method gets returned. And that bound method, basically, it goes and finds the func it knows about, and it goes and finds the self it knows about, and it passes whatever you pass to it, and it returns whatever that function call returns. That's how it happens. Okay? What's the type function for classes? Well, what is the type function for classes? The type function for classes, great talk from Glyph Lefkowitz back in 2010. Go look it online if you want. The class statement is just a way to call a function, take the result, and put it into a namespace. So that's sort of what I said, except I didn't tell you there was a function behind the scenes that actually does the work. Right? The function is called type. Oh, wait, we used type earlier and it took one argument, right? You pass it an object and it gives you the type. If you pass it 3 arguments, it assumes that they're going to be, and there's actually another version in Python 3, but ignoring that, if you pass it these 3 arguments, and the other one's very similar. Anyway, this is the function that actually gets called when a class statement is used to create a class. Okay? Type called with 3 arguments is how that works. So there are there's this one. That's what's going to get called here. So let's use the type function to build a class. Why would we want to do that? Well, because we're writing really cool libraries that thousands of people are going to benefit from. We won't do it this way, though. But we need to understand how this works if we want to do it the right way, which would probably be meta classes. So there's an init method. Sorry, there's an init function. There's an add function. They look very familiar. I call them single underscore init, single underscore add. I pass type the name and the base classes, plural, because Python is multiply inheritant. And I pass it a dictionary of names and key value pairs, right? Where the key is the name I want to show up in there, and the pair and the value is a reference to the real object I want to stick in that place, right? Done. I've just done the same thing as the class statement. Pretty simple, eh? I can use it. It works. There's proof. All right? So we pass it the name. So remember when I said that when you def and a class, they both take the name you give them and do two things with them, sort of like the import does too, right? So in a class statement, which I'm about to show you, but I want to see this first. So we have to pass it the name number if we want the class to know itself as the name number that we're going to put into the local namespace. It's just one of the things you got to do, right? So here you can see the name number goes into two places. It goes into the namespace and the class object that gets created by the type function and returned, and is what the number name in my current namespace now refers to. That object, that class object, knows about the name number. It knows about that attribute and that attribute. It might know about a doc string attribute under doc, and it knows what what classes it should be a subclass of. I suspect, actually, let me go back to there. I just noticed maybe a, not exactly typo, but I'm not sure that that is necessary in Python 3. I think it's probably not, because Python 3 you don't have to declare object as your superclass, and I didn't catch that till now. Sorry, it's not base classes, a list of base classes. When you define it anyway, yep, exactly. Okay. And of course, these all work. Okay. I think I already showed you the slide, which is that one. Hang on, let me make sure I'm not getting lost. You could tell from your handout if you look at it. Okay. So by default, classes are constructed using type. Class body is executed in a new namespace. Class name is bound locally to the result of that function. So if you pass the meta class keyword argument in the class definition line in Python 3, or make it the dunder meta class attribute in Python 2, or you inherit from an existing class that does that, then you can interfere with the way the class gets created. So similarities to decorators, right? You get to sort of stick your own behavior in between. So I'm not going to, don't quote me that this is identical to, but roughly speaking, if we say meta class equal type here, and then we have that number class, well, it's as though we didn't do anything new, right? We told Python to use type. Well, if we hadn't put meta class equal type in, Python was going to use type anyway, right? So this is just sort of making explicit what implicitly is going on behind the scenes, I believe. I don't think there's any difference. I'd love to hear if someone knows the guts behind it, if that is true. So your turn to do some exercises with the class statement. And hopefully it will help you understand meta classes sort of the way it hopefully helped you, hopefully helped you understand decorators. So just to be clear, the code you're about to do in the exercise is really bad code. It's totally nonsense code, but it strips away all the distractions of what's a meta class for and just makes you think about just the namespaces and the objects being created. That's the syntax you would use in Python 3 instead of the meta class equal. Python 2, thank you. That's Python 2 syntax. The handout has Python 3 syntax. Okay. Okay, let's go through this together now. So similar to the decorator one, I'm doing weird Python code that's pretty useless, but makes you think just about the names. So return 5 has the same signature as type, not because of name, bases, and namespace, but because it takes 3 arguments. That's all, right? And it ignores them completely and just returns 5. So I can call it with anything. It always returns the integer 5. So if I say that, I get 5, right? No surprise. And the type of that's going to be int. Sorry, my clicker just did something crazy here. So if I do class y meta class equals return 5 pass, what's that going to do? Well, remember what happens is Python's going to take all the stuff in here. It's going to take the name y and pass it as the first. It's instead of calling type on what it figures out from here, it's going to call our version of type. All right. So it's going to take y and pass it as the name, which it's going to ignore. It's going to take the, in Python 3, implied, probably takes the implied superclass object as a single tuple and passes it there. Not sure if that's implicit in Python code or in the type code. Don't know if it matters. And then it's going to take the namespace, which is just empty because I've just got this no up here, and pass that there. It's going to ignore all those. And so Python's going to call that function, and that function's return value, that's going to be what Python uses as the class object that it puts into the local namespace with the name y. And of course, what object will return 5 return? An integer object, which represents 5, right? So now if we look at y, y is just equal to 5, right? So again, that strips away all the other stuff. This is the mechanics of class creation with a meta class if you pass it a function. If you pass it that simple function. Okay. Remember decorators, I talked about functions, taking functions. Well, decorators, you can apply them to a class too. Okay. So, what's that going to do? Python is going to take this class object that it creates. There's no meta class thing in here, so it actually calls the type function, gets a real class that knows that its name is Z, it knows it has no attributes, and it knows it inherits from object. And then the decorator is going to take that object and it's going to ignore whatever it was passed and just return 6. And so now Z is going to be in the namespace, and it's going to have the value 6. Okay, so just like with decorators on functions, you can put decorators on classes. They work the same way mechanically. Okay. Here's an example of a class decorator, not a robust one, so it's not done right, but it kind of gives you a sense for what would a class decorator possibly be used for, right? And it will look somewhat familiar. So this is not the right way to do it. If you want to go write meta classes, don't follow this example. This is just to get a simple example and keep it simple, right? So here's a same as the return 6. Here's a function, takes a class. It's going to add an attribute to the class, not to the instance of the class, but to the class itself, right? It's going to keep track of the old init, create a new init, which increments that class variable, and calls the original with whatever arguments it gets called with, and then store it in new init and return the class, right? So similar to the function underscore counter function, function underscore counter class that I defined earlier, it's a similar kind of functionality, right? So let's call that decorator on the class TC, and I can now look at TC's count. I can create 2 instances of it. I create 2 instances of the class TC, which I just let drift off into nameless land where they get cleaned up. And then I can see that 2 of them were created, right? So a simple little toy example of a class decorator. So I want to show you a few things related to class methods. This is just a brief overview and then a couple examples. Standard class methods, we've talked about some of them. You're probably familiar with a few. Del is one you can control what happens when an object actually gets cleaned up. These ones all have to do, well, get attr, get attribute, set attr, you can interfere with, or del attr when you accessing attributes on an instance of a class. If these are defined, they interrupt certain ways that happens, like deleting it or setting it. Getting it if it isn't found, and getting it even if it exists. A whole bunch here that are related to in, not in, I think is that one. Iterators, which we'll look at briefly in a bit. Next is related to iterators. Set item, get item, del item, related to access with square brackets, right? So the things like lists would use. Then we've got a whole bunch of math ones. And the reason there are things like, a whole bunch of math ones. Then we also have R versions of them. So if Python has an object plus an object, it'll look for the add method on this. And if it can't find it, it'll look for the radd method on that. Radd method on that. Enter, exit, context managers. So those are just so you know, all those things that you control do some stuff. Let me show you a quick little toy example. Here's upper attr class. So what does it do? I'm going to override, or I'm going to define the dunder get attr method. And when you try to get an attribute on an instance of this class, if it's uppercase, then if the lowercase is in self.dict, so if it has an attribute which is lowercase, it's going to return it uppercased. Otherwise, it's not going to say it's not there, right? So let's just use this, right? Its dictionary is empty, so D is an instance of the class upperadder. If I create an attribute d.foo, well, nothing special happened because there's no set adder overridden here. Now, if I access it, though, the name is not, if name is up, sorry, get adder is if it can't find the attribute. So get attribute is what I got confused with for a second. So d.foo, there is now an attribute on this instance, which is foo. And so when I access it, this code is not called at all because it found the attribute in the dictionary. And that's where it found it. So that's why this code didn't get invoked. However, if I access d.foo, it can't find it in the dictionary. Then it falls back and calls my version of the code, my code, to go get the attribute. And my code says, well, if it's upper, go check to see if I have a lowercase version. If I do, return that instead in uppercase, right? So if I create an attribute foo, I can access it. If I try to access an attribute capital foo that I haven't created, it will go see if there's a lowercase one and return it in uppercase for me. Woohoo! Really useful, eh? But again, it's just an example of how you get to stick some code in there that changes how the attribute access on an instance is going to work. Right? So, and here you get this one works as well to show you that if it can't find it, it does that. And here I'm just duplicating what the normal getAdder does. So we're going to skip this optional exercise. And let me just give you the bigger picture. We've got about 25 minutes. I'm going to talk a little bit about, just show you properties very briefly, talk about iterators a little bit, talk about generators a little bit, and then give you a couple examples of some code that might stretch your thinking, some of you, in terms of how you can do things in Python. So properties in Python. If you're coming from a language like Java where getters and setters, always define them, and there's like even stuff in your editors that will make you do it, no need to do that. In Python, if you want to change the way attribute access works, here's a simple way to do it, is you define a getX and a setX and delX, and then you say x equal property, and you pass it, and you don't have to do all three. GetX, optional setX, optional delX, and then a description of it, right? So if you do this, then people can try to access, users can try to access x on the instance of this class, and it will call getX if you access it read, setX if you're trying to set it, and del if you're trying to delete it, right? So there's a simple property. p.setXFoo, of course, that works, and so does getX. That was a typo in there. Don't worry about it. The big picture's still right. So if I say p.x equal bar, you can see that setX got called, right? And if I say give me the value of x, you can see that getX got called and it returned the dunder x, which is where I'm actually storing it. And if I del, then it deletes it. Okay? So it's just for awareness. Properties are nice when you need them. Don't define them up front. Define them later if you need them, is the general advice. So on to iterators. So iterators are how for loops. The iterator protocol is the way for loops work. And there's lots of things in Python that understand the iterator protocol. Basically, in a for loop, for x in expression, what happens is, whatever that expression is, for x in foo, the for loop calls the built-in iter function. And the iter function does the following. Checks to see if the dunder iter method exists on the instance foo. If not, instance, that applies as it's a class. It just checks to see if that function is there. If it's a bound method, fine. Otherwise, it calls dunder get item, checks for get item, and if get item exists, then it returns an object that that object, when you try to iterate over, it's just going to call string at 0, 1, 2, 3. Eventually, it's going to run off the end of your sequence if it's only defining get item. It's going to get an index error, return, raise a stop iteration in its place. Okay. Thought I had another slide. No. So let's just see how this works. There's a class mylist, which has a dunder init. Just whatever you pass it, it's going to remember them. And whenever you call get item, it's going to tell you that it called it and then return it. So it's just, I've just put that in there so you can see what's going on. Right? So I can call get item 0, get item 1, get item 2, get item 3. No surprise, right? Because it's just going to try to access, it's going to take that list ABC, and it's going to put that in self.items. And then each time I call, it's just going to try to get self.items subkey. Right? So this is the way get item is usually used, of course. M square bracket 0 close square bracket. Get item gets called. Right? And then we get our index error. M doesn't have a dunder iter, but it does have a get item. So if I call the iter function, then it's going to return a new object. And that object, if I call its dunder next method, that's how the for loop actually calls the iterator, the iterable. No, the iterator, sorry. When it calls the iterable, it calls the dunder next method. And what it's going to do is it's going to turn around and try accessing element 0. And then it's going to try to access element 1, try to access element 2, try to access element 3. It's going to get an index error. But it doesn't raise an index error. It raises a stop iteration, right? So that's what makes iterators work on sequences without defining dunder next or dunder iter, is it just knows how they do. Of course, the way you'd usually use it is something like, you just pass it to a list and that happens. Or you put it in a for loop and it happens, right? So here's the way these things work. So simple little example there. I'm going to skip. And so the reason I've included these ones that I planned on skipping up front is because I want you to be able to go look at them later yourselves. And there's stuff you can learn from those I thought was useful. Okay. So we'll skip those exercises, if I can drive this thing right, and look at generators briefly, related to iterators. So list comprehensions you're all familiar with. So you may not be familiar with why they're good, though. I would quote people who argue that the reason list comprehensions are good is because they are a statement of what you want, as opposed to a statement of how you want to compute it. Right? So when you think about why should I use a list comprehension instead of a for loop, one answer is, well, because this just tells you, this is a statement of what you want. I want 2 times I for I in range, as opposed to have a for loop that, and does all the mechanics of it. So generator expression, you change the square brackets to round brackets, and you get one of these generator objects, and it has a dunder next method, and so we can just consume it, pass it to list. List will do a for loop effectively. And create that thing. Of course, if we call it, if we pass it again, it's empty. It's been exhausted. So iterators, you use them up, and they don't automatically reset, and that would be bad if they did. So here's the way you would usually call it, of course. Right? You just say for I in, and then you've got your expression there. In general, a list generator expression is better than a list comprehension because it's lazy, and anything Python's been adding support more and more over the years for lazy evaluation, which is nice for lots of reasons. Reasons including memory efficiency. Sometimes you're accessing things that are infinite, or you don't know when the next thing's going to arrive because it's over the network or whatever. So you just want some code that just gives you the next piece. Generator functions. Here's a generator function. If it's got a yield in it, it's going to turn it into a generator function. So what type is list 1, 2, 3? Trick question. It's not. You would think it would be, but this confuses people, right? I trip over this myself occasionally. Oh, right, it's just a function. What does the call to the function return? And there, the answer is it returns a generator object, right? Which makes sense. You say for I in list 1, 2, 3, and you call it, well, then it returns an object that can be iterated over, right? So let's save that object and call its dunder next, and it just gives us the yield 1, yield 2, yield 3, and stop iteration. So that's how those work. I think you all know that. It's fairly straightforward. And here's, like I said, how you would use it. Right. So what's actually going on here, right, is that when the yield, so when we call it the first time, when we call it, it returns a generator object. When we call its next method, it's basically going to start executing here, execute here, pause, return the I, whatever I has it refers to, but pause and wait for the next time next is called, right? So there's the 0. Then we call it again, and it's going to pick up right after that I, go around the loop again and do some more stuff. And it's going to do the same thing, or am I done? I'm done. So at the last time, it just falls off the end, print loop falling out. And then because we exited here, it fell off the end, or if you have a return, it basically raises a stop iteration, right? And of course, the way you'd use that is just like that, right? So that's sort of some of the mechanics of how generators work. Why would you use generator expressions? Sorry, why would you use generator functions? Well, or generators. One is because they let you do lazy evaluation. The other is because they're simpler, right? Which one of those is simpler to read, write, think about? And if you haven't yet, no, David Beasley has a great talk on generator, using these and composing these and sort of duplicating a bunch of the Unix command line arguments like grep and cat and sed, that explores how you can compose these things. And I've done quite a few times. I've written code that uses lots of small generators that are easy to test and easy to compose together, and then you get code that's like, oh, worked the first time. Well, yeah, because each piece I was able to test. And of course, the way you use them in a list comprehension, for example, is the same. Another common one that I've, working with text, you have some big file of text and you want pieces of it, and for each of those pieces you maybe need to parse some stuff out. Generator functions are great for doing that, and then you can just get out the pieces. So there's the actual contents, sample text, couple of paragraphs, whatever. If you call, you can see it just returns each of the paragraphs. Okay, so we're almost done. I think we're going to end a few minutes early. Before I forget, please, please, please go fill out the evaluation form so that we get feedback on the tutorials generally and on this tutorial specifically. I am going to, a month from now, I'm going to record something similar to this for O'Reilly. And if any feedback you give me, I will, especially this year, be reading it right away so I can see. So the more feedback you give me, the better in terms of trying to make some improvements here. There are a few glitches based on that I've noticed based on edits I made in the last couple of weeks. But I expect there are other improvements you can make, you can help me make. So if you've been using Python for a while, and this, some of what I'm about to show you here is a little bit more for people who are a little bit less, maybe beginning intermediate as opposed to intermediate. But often we learned, if Python was not your first language, you learned habits and bring baggage from whatever language you started with, or languages you started with. In Python, there are often different ways of thinking about a problem that don't occur to us because we've been trained to think by the language that we've written in. We've been trained to think of certain kinds of solutions. So a couple examples here. Toy example, but kind of neat, I think. I want to parse that. 7 plus 3 equals 10. We knew that. Let's create a calculator that you pass it 3 characters and it will calculate the result of the expression. And so here's the simplest one I can think of in Python. I'm going to import the operator module, which contains in it names, attributes in that module, the names of all the operators in the language, plus a few other interesting things. And I can call it with 7 and 3, and I get 10. All right? So it's sort of like well, reverse Polish notation. So if I take a string of 3 characters and I split it using tuple unpacking, I get the left-hand side, the operator, and the right-hand side, which are 7 plus and 3. I need to turn the 7 and the 3 into integers. All right? And then I'm going to turn them around, so I put the plus in front, so it looks a lot more like this, where I have the operation followed by the arguments. So now that is pretty close to that, but not quite the same. So how do I solve the problem of turning the plus into an operator.add? Well, you might have an if statement, but this is Python, so you don't need to have an if statement. You can have a dictionary instead, okay? And it seems simple when you see it, but a lot of times people won't think about that. You'll look at their code and go, oh, you didn't learn Python first, did you? You should have learned Python first. Anyway, no, that's not true. So what this does is it basically is a dictionary where if you access the key, which is the plus sign, it will return you the object, which is the function that does the add, right? It's a name for that thing. And so now I can just do that. And it works. So let's throw it in a function, all that stuff I just showed you, right? So no new code, no new code. That code's from there, and I just now made it into a function. So now, calc 7 plus 3, calc 9 minus 5, right? Woo! And why is this good? Well, a bunch of reasons. One is it's just simpler, and for 3, maybe not that much simpler to use this complicated data structure instead of a simple if statement. But as soon as you start adding, like especially if it's something where you've got, it's not just 3, but you've got, tens or hundreds of things you want to do, and you want to call different functions or something complex. Well, here's, the first scope creep where someone says, oh, we like your calculator, but we want to have divide. And so instead of going and changing a bunch of code, you change the data that the code is running from, like that, and it just works, right? You just extended your functionality, right? So fairly, again, toy example, but make sure you're trying to think in Python, how can I do this in Python that I couldn't do in other languages that I may be used to? And think about, because a lot of times the solutions in Python are much simpler and cleaner. Yeah, is it code or data? Who cares? Here's another example from code I wrote 10 years ago, not that, 7 years ago, where we had to parse tons of these files that had fixed offset records in some system. And so slices in Python are first-class objects. So when you access, like when you say a list square bracket 0 or 0 colon 1 or colon 3 or something like that. So these are the slices that I want to get out of the list. And so when someone tries to get an attribute, it's going to check to see if the name of that attribute is in the dictionary. If so, it's going to grab the slice to figure out which of the contents in the record to return. Otherwise, it's going to say, sorry, you don't have the attribute. All right, so now we have an unpacker for the lowercase letters, where first will always give us 0 to 3, hide will give us some others, and my name will give us some others. Some fun, so there's u dot first. Much more convenient than saying u square bracket 0, colon 3 square bracket, right? It's a readable name. It's easy to use. You don't have to put square brackets or quotes or anything else. It just makes it look like it's a different kind of object, like it's some kind of named tuple or something, right? And there's hide. Waiting for the groans in the audience? Nothing, okay. Right, so there, a quick little example. So that's the end of my tutorial. There's another optional section you can look at just in case you're not very familiar with partials or closures, some quick, simple examples on it. And I encourage you, again, to fill out the survey. You've got 10 minutes to do so. And thanks for coming, and I'll be around afterwards for questions.